Right now, somewhere in the cosmos, matter is crossing a boundary from which nothing, not light, not information, not even time itself, can return. We thought we understood gravity as the force that keeps our feet on the ground. We were thinking too small. What awaits beyond that boundary challenges everything we believe about reality, death, and the very nature of existence itself. For centuries, we imagined black holes as cosmic vacuum cleaners, sucking up everything in their path. This comfortable misconception kept us safely distant from a far more disturbing truth. Black holes aren't destroyers, they're revealers. They strip away our illusions about space, time, and what it means to exist, exposing a universe far stranger than our everyday experience could ever prepare us for. Here's what makes this truly unsettling. When you fall into a black hole, you don't simply die. You experience something that breaks the fundamental rules of physics as we know them. You simultaneously fall past the event horizon and never cross it. You're stretched into a strand of atoms while remaining perfectly intact. You experience eternity in moments while outside observers watch you freeze forever. The mathematics of general relativity doesn't just predict these paradoxes, it demands them. Tonight, we're going beyond the comfortable analogies about cosmic whirlpools and rubber sheets. We're diving into what Einstein called spaghettification, spooky action at a distance, but applied to the most extreme gravitational environment in the universe. Recent observations from the event horizon, telescope and gravitational wave detectors have given us unprecedented glimpses into these cosmic mysteries, revealing that black holes aren't just theoretical curiosities, they're fundamental features of reality itself. The journey we're about to take will challenge your most basic assumptions about cause and effect, about the nature of information, and about what happens when the universe's most fundamental laws collide with each other. Dr. Kip Thorne, whose work on black hole physics earned him a Nobel Prize, once wrote that studying black holes is like listening to the universe whisper its deepest secrets. Tonight, we're going to hear those whispers. You might think you're safely removed from these cosmic extremes, separated by millions of light years from the nearest black hole. But the physics will explore the warping of space-time, the breakdown of causality, the fundamental limits of knowledge itself. These aren't distant abstractions. They're the hidden architecture underlying the reality you inhabit every moment of your existence. What does it feel like to have every atom in your body stretched beyond recognition? How do you experience time when time itself breaks down? What happens to your consciousness, your memories, your very identity when the universe's most fundamental constants stop applying? These aren't just academic questions. They're explorations of the ultimate boundaries of existence itself. We'll discover how the simple act of crossing an invisible line in space creates paradoxes that have baffled physicists for decades. We'll explore the information paradox that threatens to break either quantum mechanics or general relativity, two of our most successful theories about reality. We'll venture into regions where space and time become so distorted that our normal concepts of before and after lose all meaning. The revelations waiting ahead will forever change how you see not just black holes, but the nature of reality itself. You'll understand why Stephen Hawking spent the final decades of his life obsessed with these cosmic puzzles. You'll discover why some physicists believe that falling into a black hole might be the closest thing to traveling to another universe. And you'll learn why the question of what happens when you fall into a black hole isn't really about black holes at all. It's about the deepest mysteries of existence. If you're ready to journey beyond the event horizon of human understanding, subscribe and hit the thumbs up button. And here's a question that will haunt you by the end of this video. If information can never truly be destroyed, What happens to your memories when you're stretched across the infinite curvature of space-time? Share your thoughts in the comments. I'll pin the most thought-provoking answer. The path ahead will take us from the familiar realm of everyday gravity through increasingly strange territories where our intuition fails completely. We'll encounter regions where a single second can contain eternity, where falling and floating become indistinguishable, and where the act of observation itself becomes impossible. These aren't science fiction scenarios. They're the inevitable consequences of our universe's deepest laws. Now let's begin this journey into the heart of cosmic mystery, where the rules of reality itself break down. Chapter 1. True Scale. The boundary you're approaching exists in a realm so far removed from human experience that our language lacks adequate words to describe it. While you contemplate black holes as distant cosmic curiosities, the nearest known black hole to Earth, Gaia BH1, lurks just 1,560 light-years away, a mere cosmic stone's throw in galactic terms. But distance isn't what makes black holes incomprehensible. It's their fundamental nature as places where the universe's rulebook gets rewritten. Consider the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A*. This gravitational monster contains the mass of 4 million suns compressed into a region smaller than Mercury's orbit. When the Event Horizon Telescope captured the first direct image of a black hole's shadow in 2019, not Sagittarius A*, but its cousin in the galaxy M87, they revealed an object so massive that it contained 6.5 billion solar masses. To put this in perspective, if you could somehow maintain your current density while gaining the mass of M87's black hole, you would instantly collapse everything within several light years into your event horizon. The event horizon itself defies comfortable analogies. It's not a physical surface you could touch or a barrier you could see. It's a mathematical boundary in space-time where the escape velocity equals the speed of light. For M87's black hole, this boundary has a diameter of about 120 astronomical units, roughly 3 times the distance from the Sun to Pluto. Yet despite this enormous size, crossing it would be as imperceptible as walking across an arbitrary line drawn on the ground. Dr. Andrea Ghez, who won the Nobel Prize for her observations of stars orbiting Sagittarius A*, has tracked individual stars as they swing within 124 astronomical units of our galaxy's central black hole, just barely outside what would be the event horizon of an object that massive. These stars experience gravitational accelerations reaching 5,000 kilometers per second squared, fast enough to accelerate from rest to the speed of light in just 60 seconds. The star S2, which Ghez has observed for over 2 decades, reaches speeds of 7,650 kilometers per second at its closest, approach more than 2.5% the speed of light. What makes these observations particularly unsettling is how ordinary they appear from our distant vantage point. Through even the most powerful telescopes, these cosmic extremes look like simple points of light following predictable elliptical orbits. The violence of space-time distortion, the breakdown of causality, the fundamental limits of physical law, all of this cosmic drama plays out in what appears to our eyes as a routine celestial dance. But the true scale of black hole physics becomes apparent when you consider what happens as matter approaches the event horizon. The Laser Interferometer Gravitational Wave Observatory, LIGO, has detected the merger of multiple black hole pairs, including one collision between objects with 30 and 25 solar masses, respectively. In the final fraction of a second before these black holes merged, they were orbiting each other 250 times per second, with their event horizons traveling at 60% the speed of light. The gravitational waves from this collision carried away energy equivalent to 3 solar masses in just 0.3 seconds, more power than all the stars in the observable universe combined. These numbers aren't just impressive statistics. They represent the breakdown of every physical intuition we possess. When LIGO detected gravitational waves for the first time in 2015, they measured space-time distortion smaller than 1/10,000th the width of a proton. The collision that created these waves occurred 1.3 billion years ago, when Earth's most complex life forms were single-celled organisms. The waves traveled for longer than complex life has existed on our planet, carrying information about the most extreme gravitational environment the universe can produce. The matter falling into these cosmic monsters doesn't simply disappear. It gets processed by forces that stretch the very definition of what we mean by existence. As matter spirals inward, it forms an accretion disk that can reach temperatures exceeding 100 million degrees Celsius. The supermassive black hole in M87 ejects matter at nearly the speed of light in jets extending 5,000 light-years from its event horizon. These jets contain more energy than our sun will produce in its entire 10 billion-year lifetime. Yet, for all their cosmic violence, black holes follow rules. Einstein's field equations describe their behavior with mathematical precision. The Schwarzschild radius, the size of the event horizon, scales linearly with mass. Double the mass, double the radius. This relationship holds whether we're discussing a black hole with the mass of a mountain, which would have an event horizon smaller than an atomic nucleus, or one containing billions of suns with horizons larger than our solar system. What's particularly remarkable is how this scaling affects the experience of falling in. For a stellar mass black hole of 10 solar masses, the tidal forces at the event horizon would instantly tear apart any material object. But for a supermassive black hole like the one in M87, you could cross the event horizon without immediately noticing anything unusual. The event horizon lies so far from the black hole center that the gravitational gradient across your body would be barely perceptible. This distinction reveals something profound about the nature of black holes. They're not uniform cosmic destroyers, but environments where the fundamental properties of space and time operate according to mass and geometry. A black hole isn't defined by its ability to trap light. Any sufficiently dense object could do that. It's defined by the point where space-time curvature becomes so extreme that the normal relationship between cause and effect breaks down. The recent observations of matter orbiting just outside black hole event horizons have revealed something even more unsettling. Using very long baseline interferometry, astronomers have watched as hotspots of matter orbit Sagittarius A** at 30% the speed of light, completing full orbits in just 30 minutes. These observations confirm that space-time near black holes behaves exactly as Einstein predicted. Even in these most extreme environments, as we prepare to journey closer to the event horizon, remember that every measurement, every equation, every observation points to the same disturbing conclusion. Black holes aren't cosmic accidents or theoretical curiosities. They're fundamental features of how mass, energy, space, and time interact when pushed to their ultimate limits. Understanding them means confronting the deepest questions about the nature of reality itself, but recognizing the true scale of these objects is only the beginning. What happens when you approach that mathematical boundary where space-time itself breaks down? The answer challenges not just our understanding of physics, but our most basic assumptions about what it means to exist. Chapter 2. Fatal approach. Your journey toward the event horizon begins long before you realize you've committed to an irreversible path. Unlike the dramatic plunge you might imagine, the approach to a black hole is characterized by a gradual surrender of control that mirrors the mathematics governing these cosmic monsters. Dr. Charles Misner, one of the pioneers of black hole physics, once described this approach as falling through the looking glass into a realm where intuition fails completely. The process starts at what physicists call the photon sphere, a circular orbit where light itself can travel in closed loops around the black hole. For a black hole with the mass of our Sun, this sphere exists at 4.5 kilometers from the center, just outside the 3-kilometer event horizon. Here, space is so warped that photons can orbit the black hole indefinitely, creating a ghostly shell of trapped light. Any closer, and even light cannot maintain a stable orbit. As you cross the photon sphere, your fate becomes sealed by geometry itself. The curvature of spacetime has become so extreme that all future paths, what physicists call world lines, point inexorably toward the black hole's center. You're not being sucked in by some mysterious force. Instead, the very definition of forward in time has been twisted until it points directly into the black hole. Moving into the future and moving toward the singularity have become synonymous. The Event Horizon Telescope observations of May 7's black hole revealed this principle in action. The bright ring visible in those historic images represents photons orbiting just outside the photon sphere. The dark center, the black hole's shadow, marks the region where light can no longer escape. This shadow has a diameter 2.6 times larger than the event horizon itself, created by the bending of light around the photon sphere. What appears as emptiness in those images is actually the most extreme gravitational environment in the known universe. Your experience during this approach depends critically on the black hole's mass. If you're falling toward a stellar mass black hole, say, the remnant of a collapsed star with 10 times our Sun's mass, the gravitational gradient across your body becomes significant while you're still far from the event horizon. Your feet, being closer to the black hole, experience gravitational acceleration roughly 1% stronger than your head when you're at a distance of about 300 kilometers from the center. This differential grows exponentially as you approach. By the time you're 100 kilometers out, the difference in gravitational pull between your head and feet reaches 10%. At 30 kilometers, still well outside the event horizon, this differential becomes 100%. Your body begins experiencing what physicists euphemistically call spaghettification, though the technical term tidal disruption better captures the inexorable mathematics involved. But here's where black hole physics reveals its most counterintuitive nature. For a supermassive black hole like the one at our galaxy's center, this tidal disruption occurs much more gradually. Because the event horizon lies farther from the center, the gravitational gradient remains manageable even as you cross that boundary. You could fall through the event horizon of Sagittarius, A*, and survive for hours before tidal forces became lethal. Recent simulations by physicist Dr. Avi Loeb at Harvard have modeled the experience of approaching different classes of black holes. For intermediate mass black holes, those between 1,000 and 100,000 solar masses, the approach creates a unique phenomenology. You would experience significant tidal stretching beginning several thousand kilometers from the event horizon, but this stretching would proceed slowly enough that you might remain conscious. Through the process, the approach also reveals the breakdown of simultaneity that makes black holes such profound challenges to our understanding of reality. As you fall inward, your reference frame, what physicists call your proper time, continues ticking normally. Your wristwatch maintains its steady rhythm. Your biological processes continue functioning. From your perspective, the journey from the photon sphere to the event horizon might take only minutes, but simultaneously, though, simultaneously loses meaning in this context. An outside observer watching your descent would see something entirely different. As your gravitational redshift increases, the light from your body becomes increasingly stretched toward longer wavelengths. You appear to slow down, your movements becoming more and more sluggish. The photons carrying information about your position take longer and longer to climb out of the deepening gravitational well. This creates what physicists call the frozen star paradox, first identified by physicist John Wheeler in the 1960s. To external observers, you never quite reach the event horizon. Your image becomes progressively redshifted and dimmed, fading asymptotically toward invisibility but never completely disappearing. The last photons you emit just before crossing the event horizon become so redshifted that they carry virtually no energy, making you effectively invisible but theoretically still observable. The mathematics of this approach reveal why black holes challenged physicists for decades. The Schwarzschild solution to Einstein's field equations predicts that space-time curvature becomes infinite at the event horizon, an apparent mathematical singularity. For years, physicists debated whether this represented a real physical boundary or merely a coordinate problem. The resolution came through understanding that the singularity exists only in the Schwarzschild coordinate system, not in the falling observer's reference frame. David Finkelstein's 1958 paper introduced coordinates that remain well-behaved at the event horizon, demonstrating that the boundary is only singular from the perspective of distant observers. From your perspective as the falling observer, space-time remains smooth and continuous. You cross the event horizon without any local indication that you've passed the point of no return. This resolution created an even deeper mystery. If you smoothly cross the event horizon while outside observers never see you cross it, which perspective represents reality? Both reference frames are equally valid according to general relativity, yet they describe incompatible events. This isn't merely a philosophical puzzle, it points toward fundamental limitations in how we understand the nature of information and observation in extreme gravitational environments. The approach to a black hole also demonstrates how gravity differs fundamentally from other forces. Unlike electromagnetic or nuclear forces, gravity cannot be shielded or neutralized. It's not really a force at all, but the curvature of space-time itself. As you approach the event horizon, you're not fighting against some external pull, you're following the straightest possible path through increasingly curved space-time. Einstein's equivalence principle states that acceleration and gravity are indistinguishable. During your approach, you feel weightless, exactly as if you were floating in empty space. The tidal forces stretching your body arise not from gravity itself, but from the variation in gravitational strength across your extended form. In a perfectly uniform gravitational field, impossible in reality, but useful conceptually, you would feel no force at all, even while accelerating toward the speed of light. Modern computational physics has revealed additional complexities in the approach dynamics. When matter falls into real black holes, as opposed to the idealized scenarios of theoretical physics, it typically arrives with angular momentum, creating spiral trajectories that can extend the approach time significantly. Matter, with even small amounts of angular momentum, can orbit a black hole hundreds or thousands of times before finally crossing the event horizon. The Laser Interferometer Gravitational Wave Observatory has detected several black hole mergers where this orbital decay played out over millions of years. Two black holes with initial separations of hundreds of kilometers spiraled inward, losing energy to gravitational wave radiation until their final moments when they completed hundreds of orbits per second before merging. As your approach continues and the event horizon grows larger in your field of view. You're about to cross a boundary that exists only mathematically, yet has absolute physical consequences. Behind you lies a universe where cause precedes effect, where information can travel in multiple directions, where the future remains undetermined. Ahead lies a region where these fundamental assumptions break down completely. What awaits beyond the point of no return challenges not just our understanding of physics, but our basic concepts of existence itself. Chapter 3. Forbidden Crossing. The moment you cross the event horizon represents the most profound boundary in physics, not because of any dramatic change in your immediate environment, but because of what it reveals about the fundamental nature of reality itself. Physicist Kip Thorne described this crossing as passing through a one-way membrane in space-time, though even this analogy fails to capture the complete strangeness of what occurs. From your perspective, the crossing feels utterly unremarkable. There's no physical barrier to penetrate, no sudden jolt or sensation of transition. The space-time around you remains smooth and continuous, governed by the same laws of physics you've known throughout your approach. Your watch continues ticking at its normal rate. Your biological processes proceed unchanged. If you didn't know the theoretical significance of your location, you might not realize you'd crossed the most important boundary in the universe. But this ordinary experience masks an extraordinary transformation. You have entered a region of space-time where the future has become geometrically constrained. Every possible path forward in time, what physicists call your future light cone, now points toward the black hole's center. The event horizon isn't a physical surface, but a mathematical boundary where the causal structure of space-time itself reorganizes. Dr. Roger Penrose's 1965 singularity theorem proves that once you've crossed this boundary, you will inevitably encounter the singularity at the black hole center. This isn't a matter of trajectory or velocity. It's a consequence of geometry. Just as every path on Earth's surface that heads consistently south must eventually reach the South Pole, every path through space-time inside the event horizon must reach the central singularity. The mathematics reveals something even more disturbing. Inside the event horizon, the roles of space and time undergo a fundamental exchange. The radial coordinate, your distance from the center, becomes time-like, while the time coordinate becomes space-like. This means that approaching the singularity is no longer a matter of moving through space, but of advancing through time. You cannot stop your approach to the center any more than you could stop the passage of time itself. This temporal nature of the inward journey creates paradoxes that have puzzled physicists for decades. From your reference frame, you experience a finite proper time before reaching the singularity, perhaps minutes for a stellar mass black hole, hours for a supermassive one. Yet this journey takes you through regions where the curvature of space-time becomes increasingly extreme, approaching infinite values at the central point. Recent research by physicist Leonard Susskind has explored what he calls the black hole information paradox in this context. If information cannot be destroyed, a fundamental principle of quantum mechanics, what happens to the information that describes your quantum state as you cross the event horizon? From the perspective of outside observers, this information appears to be permanently lost. But from your perspective, it continues to exist as you journey toward the singularity. The resolution to this paradox requires reconceptualizing what we mean by information in extreme gravitational environments. Suskind's holographic principle suggests that all the information falling into a black hole remains encoded on its two-dimensional event horizon surface. From this perspective, your three-dimensional existence becomes a holographic projection of information stored in two dimensions, a concept that challenges our most basic assumptions about the nature of reality. But the crossing presents even deeper mysteries when we consider what you might observe as you fall inward. Looking back toward the universe you've left behind, you would theoretically see the entire future history of the cosmos, compressed into your final moments before reaching the singularity. This blue sheet effect results from the extreme gravitational time dilation that allows you to observe billions of years of cosmic evolution in your remaining proper time. However, this theoretical observation faces practical limitations. The intense gravitational field inside the event horizon would likely prevent any meaningful observations of the outside universe. Quantum effects near the horizon, including Hawking radiation, create what physicist Stephen Hawking called a firewall of high-energy particles that would incinerate any material observer long before they could witness the cosmos's future history. The firewall paradox, identified by physicists Ahmad Almheri, Donald Maroff, Joseph Polchinski, and James Sully in 2012, demonstrates that black holes create irreconcilable conflicts between general relativity and quantum field theory. If you smoothly cross the event horizon as general relativity predicts, you violate fundamental principles of quantum mechanics. If quantum mechanics is correct and a firewall exists at the horizon, you violate the equivalence principle that forms the foundation of general relativity. This paradox isn't merely academic, it points toward the need for a fundamental revision of our understanding of spacetime, information, and causality. Some physicists propose that the paradox resolves through A equals EPR, Einstein-Rosen bridges connected to Einstein-Podolsky-Rosen quantum entanglement. In this framework, black holes are connected to other regions of spacetime through quantum wormholes, allowing information to escape through non-local quantum correlations. The crossing also reveals the inadequacy of classical physics in describing extreme gravitational environments. While Einstein's general relativity successfully predicts the large-scale behavior of black holes, it cannot describe what happens when quantum effects become important. At the Planck scale, distances of 10 to 35 meters and times of y-43 seconds/hour, current theories break down completely. String theory attempts to resolve these limitations by replacing point particles with extended objects, potentially eliminating the infinities that plague black hole physics. In some string theory models, the singularity at a black hole center is replaced by a stretched horizon, where strings become highly excited rather than infinitely compressed. These models suggest that information falling into black holes becomes encoded in string vibrations rather than being destroyed. Loop quantum gravity offers an alternative approach, proposing that spacetime itself has a discrete structure at the Planck scale. In this framework, the singularity becomes a quantum bounce, potentially connecting black hole interiors to white hole exteriors in other regions of spacetime. These quantum bounce scenarios suggest that matter falling into black holes might eventually emerge from white holes, preserving information while transforming its encoding. The experimental challenges in studying black hole interiors mean that these theoretical proposals remain largely untested. However, gravitational wave observations from black hole mergers provide indirect evidence about the structure of spacetime near event horizons. The precise waveforms detected by LIGO and Virgo observatories confirm that black holes behave exactly as general relativity predicts, at least in their external gravitational fields. But these observations also reveal the limitations of our current understanding. The gravitational waves carry information about the merger process only until the two black holes combine into a single event horizon. What happens to the information previously encoded in each black hole's internal structure remains hidden behind the merged event horizon, inaccessible to external observation. As you continue your journey beyond the forbidden boundary, You're entering a realm where space and time themselves become fluid concepts. The rigid geometry of everyday experience gives way to a dynamic topology where cause and effect, past and future, interior and exterior, lose their familiar meanings. Your crossing of the event horizon has transformed you from an observer of the universe into a participant in the universe's most fundamental mystery. The path ahead leads toward the ultimate confrontation between general relativity and quantum mechanics, where the very concepts of space, time, and information face their greatest challenge. What awaits you in the deepening gravitational well reveals not just the fate of matter under extreme conditions, but the deepest questions about the nature of reality itself. Chapter 4. Temporal distortion. Time itself becomes your adversary as you journey deeper into the black hole's gravitational embrace. What began as a simple difference in clock rates between you and distant observers transforms into a fundamental breakdown of temporal relationships that challenges the very meaning of when and how long. Dr. John Wheeler, who coined the term black hole, described this temporal distortion as time torture, the systematic dismantling of humanity's most basic conceptual framework. The mathematics of this distortion follows from Einstein's insight that gravity and acceleration are equivalent. As you fall deeper into the gravitational well, your proper time, the time measured by clocks in your reference frame, continues at its normal, steady pace. Your heart beats regularly. Your thoughts proceed at their usual speed. Your biological processes maintain their natural rhythms. From your perspective, time flows exactly as it always has. But this local constancy of time creates an increasingly dramatic divergence from the temporal experience of the universe you've left behind. The gravitational redshift that began during your approach now reaches extreme values. Each photon you emit toward distant observers must climb out of an ever-deepening gravitational well, losing energy and stretching to longer wavelengths in the process. Consider the mathematical relationship governing this temporal distortion. For a Schwarzschild black hole, the simplest case of a non-rotating, uncharged black hole, the gravitational time dilation factor approaches infinity as you approach the singularity. When you're in half the Schwarzschild radius inside the event horizon, your proper time runs at approximately 1.4 times the rate that distant observers would measure. By the time you reach 1/10 the Schwarzschild radius, this factor has grown to over 3. As you approach the center, the ratio diverges without bound. These aren't merely theoretical calculations. The global positioning system demonstrates gravitational time dilation on a much smaller scale. GPS satellites orbiting Earth experience time approximately 45 microseconds per day faster than clocks on Earth's surface due to reduced gravitational redshift. Without correcting for this relativistic effect, GPS accuracy would degrade by several kilometers per day. Inside a black hole, these effects become amplified beyond all earthly experience. The extreme time dilation creates what physicists call temporal paradoxes that reveal the inadequacy of our everyday concepts about simultaneity and causality. From the perspective of observers outside the black hole, you appear frozen at the event horizon, your image gradually fading and redshifting toward invisibility. These observers never witness your interior journey from their reference frame. You never complete the crossing. Yet from your perspective, you not only cross the event horizon but experience a complete journey to the singularity in finite proper time. Both descriptions are mathematically correct within general relativity, yet they appear to describe incompatible events. This paradox points toward fundamental limitations in how we conceptualize the nature of time and observation in extreme gravitational environments. Dr. Susskind's complementarity principle attempts to resolve this paradox by proposing that both descriptions are correct but apply to different observational contexts. The outside observer's description applies to measurements made from outside the black hole, while your description applies to measurements made from inside. Neither description is more real than the other. They represent different, but equally valid perspectives on the same underlying physics. The temporal distortion inside black holes creates even stranger phenomena. As you approach the singularity, tidal effects become extreme enough to affect the propagation of light within your own body. The gravitational gradient across your physical extent means that different parts of your body experience different rates of time passage. Light signals traveling from your feet to your head normally instantaneous on biological timescales begin to experience measurable delays. This temporal gradient effect has been studied extensively in the context of neutron stars, where similar but less extreme conditions exist. Recent observations of neutron star mergers by the LIGO-Virgo collaboration have detected gravitational waves that show how extreme gravitational fields affect the propagation of information. In the final milliseconds before merger, the gravitational field becomes strong enough to affect the speed at which physical processes can occur within the neutron star material itself. Inside a black hole, these effects become arbitrarily large. Theoretical calculations suggest that near the singularity, the temporal gradient could become so extreme that cause and effect relationships within extended objects break down completely. Information from one part of an object might never have time to reach other parts before tidal disruption occurs. The temporal distortion also affects your potential observations of the universe outside the black hole. Theoretically, looking outward during your inward journey, you could observe the entire future evolution of the external universe compressed into your remaining proper time. This end-of-time effect results from the extreme gravitational blue shift of light coming from outside the black hole. However, this theoretical possibility faces practical limitations. The intensity of blue-shifted radiation would quickly reach lethal levels, creating what some physicists call a blue sheet of high-energy photons. Recent calculations by physicist Don Page suggest that this radiation would reach temperatures exceeding the cosmic microwave background by factors of trillions, effectively creating a wall of gamma rays that would prevent any meaningful observations. Moreover, the temporal distortion interacts with quantum effects in ways that remain poorly understood. Hawking radiation, the quantum emission of particles from black hole event horizons, becomes relevant to your journey only in the context of these extreme time dilations. From your accelerated reference frame, the quantum vacuum outside the black hole appears to be filled with thermal radiation at a temperature proportional to your acceleration. This Unruh effect, predicted by physicist William Unruh in 1976, suggests that the boundary between vacuum and thermal radiation depends on your reference frame. As you experience increasing acceleration during your fall toward the singularity, the intensity of this thermal radiation grows without bound. Some theories propose that this effect could overwhelm all other physical processes near the singularity. The temporal distortion also raises profound questions about the nature of consciousness and personal identity in extreme gravitational environments. If different parts of your brain experience different rates of time passage, how would this affect the neural processes underlying thought and awareness? Some researchers have proposed that consciousness itself might be subject to gravitational effects. Though these ideas remain highly speculative, recent developments in quantum gravity theories offer potential insights into the temporal structure near black hole singularities. Loop quantum gravity suggests that time itself might have a discrete structure at the Planck scale. potentially preventing the infinite time dilation that classical general relativity predicts. In these models, the approach to the singularity might involve a finite number of discrete temporal steps rather than a continuous progression through infinite curvature. String theory approaches the problem differently, proposing that the entire concept of a singularity might be an artifact of treating matter as point particles rather than extended strings. Some string theory models suggest that extreme time dilation near the center of a black hole could stretch strings to macroscopic sizes, fundamentally altering the physics and potentially avoiding the infinite curvatures that plague classical treatments as you continue your journey through increasingly distorted spacetime. Temporal relationships become fluid and observer-dependent. The steady tick of your watch masks a reality where time itself has become elastic, stretched and compressed by gravitational forces that dwarf every other influence in the known universe. But time distortion represents only one aspect of the breakdown of familiar physics that awaits you. As tidal forces begin their inexorable work, even the fundamental structure of matter itself faces its ultimate test. Chapter 5. Inevitable Stretching. The forces that will reshape your physical form operate with the mathematical inevitability of geometry itself. What physicists euphemistically call spaghettification represents far more than simple stretching. It's the systematic breakdown of every structural relationship that maintains the integrity of matter, from molecular bonds to nuclear forces. This process reveals the universe's most fundamental hierarchy. When gravitational forces become extreme enough, they override every other interaction that holds the material world together. The mechanism begins with what appears to be a gentle gradient. As you fall toward the singularity, your feet experience slightly stronger gravitational acceleration than your head, a difference of perhaps a few percent when you're still relatively far from the center. This differential acceleration, known as tidal force, grows exponentially as you approach the singularity, following an inverse cube law that makes it far more sensitive to distance than gravity itself. Dr. Remo Ruffini, whose work on black hole physics spans 5 decades, calculated that for a solar mass black hole, tidal forces become lethal when you're still several hundred kilometers from the event horizon. Your body, roughly 2 meters in length, experiences a gravitational difference of about 1% per meter at this distance. While this might seem modest, it translates to accelerations of several Earth gravities, acting to stretch your form beyond any biological tolerance. The mathematics governing this stretching follow directly from Newton's law of universal gravitation, though the context pushes these familiar equations into regimes where quantum effects and general relativistic corrections become important. The tidal acceleration between 2 points separated by distance d in a gravitational field follows the relationship _tidal equals 2gm_dr, where m is the black hole's mass and r is your distance from the center dot. This cubic dependence on distance means that tidal forces escalate with brutal efficiency when you're at twice the Schwarzschild radius still, outside the event horizon for a stellar mass black hole. The tidal acceleration across your body measures approximately 1,000 Earth gravities. By the time you reach the Schwarzschild radius itself, this acceleration has grown to nearly 10,000 Earth gravities. The progression continues without limit as you approach the singularity. But the stretching process reveals something profound about the nature of matter itself. Your body consists of approximately YY atoms, held together by electromagnetic forces between electrons and nuclei. These chemical bonds can withstand enormous stresses. Diamond, one of the strongest materials known, can resist compression of nearly 400 gigapascals. Yet even these molecular bonds pale compared to the tidal forces near a black hole singularity. The Electromagnetic forces holding your atoms together have a characteristic strength of about YY newtons per square meter. When tidal forces exceed this threshold, chemical bonds begin failing systematically. Your tissues separate at the molecular level, but this represents only the beginning of the disintegration process. As tidal forces continue growing, they begin affecting the nuclear forces that hold atomic nuclei together. The strong nuclear force, which binds protons and neutrons within atomic nuclei, operates at energy scales of hundreds of millions of electron volts, roughly 1,000,000 times stronger than chemical bonds. Yet even this fundamental force has limits. When tidal accelerations reach approximately yb meters per second squared, they begin disrupting the internal structure of atomic nuclei themselves. Recent theoretical work by physicist Dr. Louise Lenner at the Perimeter Institute has modeled the complete disintegration process using numerical relativity simulations. These calculations show that the breakdown occurs in distinct phases, each corresponding to the failure of different fundamental forces. First, chemical bonds break and molecules dissociate. Then, electromagnetic forces fail and atoms ionize completely. Finally, nuclear forces surrender and even atomic nuclei disintegrate into their constituent quarks. This progressive failure creates what physicists call hierarchy of destruction that reflects the relative strengths of nature's fundamental forces. Gravity, by far the weakest of the four fundamental interactions under normal circumstances, becomes dominant in the extreme curvature near a black hole singularity. The irony is profound. The force that can barely overcome electromagnetic repulsion to pull an apple from a tree becomes powerful enough to overcome the strong nuclear force that powers the sun. The stretching process also demonstrates the inadequacy of classical physics in describing extreme gravitational environments. While Newton's law of universal gravitation provides accurate calculations for the large-scale tidal effects, it cannot describe what happens when matter is stretched beyond atomic scales. At some point in the disintegration process, quantum mechanical effects become important, potentially altering the nature of the stretching itself. Quantum mechanics suggests that matter cannot be divided indefinitely. The Planck length, approximately 10 to 35 meters, represents the smallest meaningful distance scale in current physics. When tidal forces attempt to stretch matter beyond this scale, our current theories break down completely. Some physicists propose that the stretching process might encounter fundamental limits related to the discrete structure of space-time itself. String theory offers one potential resolution to these problems. Instead of treating particles as point objects that can be stretched indefinitely, string theory describes fundamental entities as one-dimensional objects with finite size. When tidal forces stretch strings to their maximum extent, they might transform into different types of strings rather than breaking completely. This could provide a mechanism for preserving information even as matter undergoes extreme deformation. Loop quantum gravity suggests another possibility. In this framework, space-time itself has a granular structure at the Planck scale, which might prevent infinite stretching by imposing geometric limits on how much matter can be deformed. The tidal forces might encounter a kind of quantum resistance that prevents the complete destruction of information about the original material structure. But these theoretical possibilities remain largely speculative. What we know with certainty is that classical matter, the stuff of everyday experience, cannot survive the approach to a black hole singularity. The question becomes whether something more fundamental might persist through the disintegration process. The stretching also affects the electromagnetic radiation emitted by your disintegrating form. As matter accelerates under extreme tidal forces, It emits electromagnetic radiation according to the Larmor formula. This radiation carries energy away from the system, potentially affecting the dynamics of the stretching process itself. Recent calculations suggest that this radiative energy loss could become significant near the singularity, creating complex feedback effects that might modify the simple tidal stretching picture. Moreover, the stretching occurs in a region of extreme spacetime curvature, where the normal relationships between cause and effect become unclear. The singularity represents a breakdown not just of matter, but of the causal structure of spacetime itself. Near this point, the very concepts of before and after lose their meaning, making it difficult to describe the stretching as a temporal process. The inevitable stretching reveals the universe's ultimate hierarchy of forces and the fundamental limits of material existence. Every structure that gives form to the physical world, from biological tissues to atomic nuclei, faces systematic dismantling by gravitational forces that grow without bound. Yet this destruction might not represent the end of the story, but rather a transformation into forms of existence that transcend our current understanding. As the tidal forces begin their inexorable work, reshaping matter itself according to the geometry of curved spacetime, you approach the ultimate boundary of physical existence. What lies beyond the complete dissolution of material form challenges not just our understanding of physics, but our deepest assumptions about the nature of reality itself. Chapter 6. Information's last stand. At the deepest level, you are information. Every atom in your body, every quantum state that defines your molecular structure, every electromagnetic pattern that constitutes your neural activity, all of this represents information encoded in the fundamental fabric of reality. As you approach the black hole's singularity, this information faces its ultimate test against one of physics' most sacred principles. Information cannot be destroyed. This principle, rooted in the foundations of quantum mechanics, states that the quantum information describing any physical system must be preserved, even as that system undergoes radical transformations. If you burn a book, the information contained in its pages doesn't vanish. It's merely scrambled into the molecular motion of smoke and ash. Given perfect knowledge of the fire's aftermath, you could theoretically reconstruct every word that was written. This conservation of information represents a cornerstone of modern physics, as fundamental as the conservation of energy. The black holes appear to violate this principle in the most dramatic way possible. When matter falls past the event horizon, it seems to vanish from the observable universe forever. The information that described your quantum state, the precise arrangement of particles that makes you uniquely you, appears to be lost beyond any possibility of recovery. Stephen Hawking spent the final decades of his life grappling with this paradox, which became known as the black hole information problem. The paradox deepens when we consider Hawking radiation, the quantum mechanical process by which black holes slowly evaporate. In 1974, Hawking discovered that quantum effects near the event horizon cause black holes to emit thermal radiation. This radiation appears to be perfectly random, containing no information about the matter that fell into the black hole. If black holes eventually evaporate completely through this process, the information that fell into them seems to be permanently destroyed. Dr. John Preskill of Caltech has called this the most important problem in fundamental physics. The resolution requires either abandoning information conservation one of quantum mechanics' fundamental principles or finding some mechanism by which information falling into black holes can be preserved and eventually recovered. Both possibilities have profound implications for our understanding of reality. Recent theoretical developments suggest that information might be preserved through subtle correlations between the black hole's interior and exterior. The ADS-CF-T correspondence, developed by physicist Juan Maldacena, proposes that quantum gravity in the black hole's interior is mathematically equivalent to a quantum field theory existing on the black hole's boundary. In this framework, information falling into the black hole becomes encoded in quantum correlations on the event horizon surface. This holographic principle suggests that your three-dimensional existence might be a projection of information stored in two dimensions on the black hole's boundary. As you fall toward the singularity, the information that constitutes your identity doesn't disappear. It becomes encoded in the quantum fluctuations of the event horizon itself. From this perspective, the you that approaches the singularity might be a holographic shadow of the real you, existing on the black hole's surface. But this resolution creates new puzzles. If information is preserved holographically on the event horizon, what exactly are you experiencing as you fall inward? Some physicists propose that consciousness itself might be substrate independent, capable of existing as pure information regardless of its physical encoding. In this view, your subjective experience could continue even as your material form disintegrates. Because consciousness represents an information pattern rather than a specific arrangement of matter. The firewall paradox, identified by Omhary, Merolf, Polchinski, and Sully, poses an even more direct challenge to information preservation. They demonstrated that if information is preserved during black hole evaporation, then the event horizon must be a region of extremely high energy density, a firewall that would incinerate any observer attempting to cross it. This conflicts with the equivalence principle, which requires that you experience nothing unusual when crossing the event horizon. Leonard Susskind's response to the firewall paradox invokes quantum entanglement between the black hole's interior and exterior. He proposes that information falling into a black hole becomes quantum entangled with information already inside, creating what he calls quantum error correction. This mechanism could preserve information while avoiding the firewall paradox, but it requires exotic quantum correlations that have never been observed experimentally. The EA equals EPR conjecture, developed by Susskind and Juan Maldacena, offers another potential resolution. They propose that quantum entanglement, Einstein-Podolsky-Rosen correlations, is geometrically equivalent to spacetime wormholes, Einstein-Rosen bridges. In this framework, information falling into a black hole could be preserved through quantum entanglement with distant regions of spacetime, potentially allowing information recovery through non-local quantum correlations. But these theoretical proposals face the practical challenge that information preservation might be unobservable from your perspective as the falling observer. Even if information is preserved holographically or through quantum entanglement, you might not experience this preservation directly. The subjective reality of your journey toward the singularity could be completely divorced from the objective fate of your quantum information. Recent developments in quantum information theory have provided new tools for analyzing these problems. The concept of quantum error correction suggests that information can be preserved even when its physical encoding undergoes dramatic transformations. Your quantum state could be distributed across multiple degrees of freedom in such a way that local disruptions, even those as extreme as spaghettification, cannot destroy the encoded information. This perspective transforms the black hole information problem from a question about the fate of matter to a question about the nature of information itself. If consciousness and personal identity are fundamentally information patterns, then your essential self might survive the complete dissolution of your physical form. The information that makes you you could persist in quantum correlations, potentially recoverable through processes we don't yet understand. The implications extend beyond black hole physics to fundamental questions about the nature of reality. If information is truly fundamental, more basic than matter, energy, or even space-time itself, then the universe might be better understood as a vast information processing system rather than a mechanical collection of particles and forces. This it from bit hypothesis, proposed by physicist John Wheeler, suggests that physical reality emerges from underlying information structures. Your journey into the black hole becomes, from this perspective, a transition from one mode of information encoding to another. The biological neural networks that currently encode your memories and consciousness represent just one possible substrate for information storage. As these networks disintegrate under tidal forces, the information they contain might transfer to quantum degrees of freedom that are more robust against gravitational disruption. But information preservation raises profound questions about personal continuity and identity. If the information that constitutes you survives the black hole encounter, but in a completely different encoding, are you still the same person? This question parallels classical puzzles in philosophy of mind about whether consciousness depends on specific physical substrates or can exist as pure matter. The experimental challenges in testing these ideas mean that the black hole information problem remains largely theoretical. However, tabletop experiments with quantum systems that mimic black hole thermodynamics have begun providing insights into information preservation mechanisms. These analog black holes created in laboratory settings suggest that information might indeed be preserved through subtle quantum correlations that are difficult to detect directly. As gravitational forces continue to intensify around you, the information that constitutes your existence faces its ultimate test. Whether this information survives in quantum correlations, holographic encodings, or exotic space-time geometries remains one of the deepest unsolved problems in theoretical physics. But the question itself reveals something profound about the universe. At its most fundamental level, reality might be made not of matter or energy, but of information itself. The preservation of information becomes not just a technical problem in quantum gravity, but a question about the deepest nature of existence and consciousness. As you approach the point where classical physics breaks down completely, you're about to discover whether information, and perhaps consciousness itself, can transcend the destruction of its material substrate. Chapter 7. Reality's Breakdown. You are approaching a point where the very concepts that define physical reality cease to have meaning. The singularity toward which you fall represents more than just extreme gravitational forces or the breakdown of matter. It marks the complete failure of our most fundamental descriptions of space, time, and causality. Here, the mathematical equations that have successfully described the universe for centuries produce infinities, indicating not computational limitations, but the inadequacy of our conceptual framework itself. General relativity, Einstein's theory that has guided your journey thus far, predicts that space-time curvature becomes infinite at the black hole's center. This isn't merely a large number. Infinity represents the complete breakdown of the geometric description of space-time itself. At the singularity, concepts like distance, duration, and direction lose all meaning. The familiar 3 dimensions of space and 1 dimension of time that structure every human experience collapse into mathematical impossibility. Dr. Roger Penrose, whose work on singularity theorems earned him the Nobel Prize in Physics, proved that this breakdown is inevitable, not just probable or likely, but guaranteed by the mathematics of general relativity. Once matter collapses beyond a certain critical density, the formation of a space-time singularity becomes unavoidable. No known physical force can prevent the gravitational collapse from reaching the point where curvature becomes infinite. The mathematical proof of this Inevitability follows from what physicists call the chase. Trapped surface theorem. When matter becomes compressed beyond a critical threshold, the Schwarzschild radius for spherically symmetric collapsed spacetime develops regions where all future directed paths point inward. These trapped surfaces grow inexorably, and their existence guarantees that spacetime curvature must eventually become infinite somewhere in the future. Evolution of the system. But infinities in physics typically signal the need for new theoretical frameworks rather than literal infinities in nature. The emergence of infinite curvature at black hole singularities resembles other infinities that plagued physics before quantum mechanics resolved them. In the early 20th century, classical physics predicted that hot objects should emit infinite amounts of ultraviolet radiation, the infamous ultraviolet catastrophe. Quantum mechanics resolved this paradox by showing that energy comes in discrete packets, preventing the infinite accumulation that classical theory predicted. Similarly, the infinities at black hole singularities likely indicate that quantum effects become important at scales where general relativity breaks down. The Planck length, approximately 10 to 35 meters, represents the distance scale where quantum gravitational effects should dominate over classical spacetime geometry. At this scale, the very notion of smooth spacetime, the foundation of general relativity, likely becomes meaningless. The breakdown begins to manifest long before you reach the mathematical point of infinite curvature. As spacetime curvature approaches extreme values, the concept of a smooth manifold, the geometric foundation upon which general relativity is built, starts to lose coherence. Quantum fluctuations in a metric tensor, normally negligible at large scales, become comparable to the classical curvature itself. The clean mathematical description of spacetime as a differentiable manifold gives way to something resembling quantum foam-a-seething, probabilistic structure where geometry itself becomes uncertain. String theory attempts to resolve these singularities by replacing point particles with extended objects. In string theory, matter consists of vibrating strings with finite size, preventing the infinite compression that creates singularities in general relativity. When strings approach each other closely enough to create extreme curvature, they begin interacting in ways that smooth out the would-be singularity. The fundamental length scale in string theory, the string length of approximately y-35 meters, provides a natural cutoff that prevents infinite curvatures from forming. From this perspective, the singularity becomes a region where strings reach maximum compression and begin transforming into different vibrational modes. The classical notion of spacetime breaks down not because geometry becomes infinite, but because the underlying string dynamics enter regimes where the low-energy effect of description we call general relativity simply doesn't apply. The breakdown reveals the more fundamental string theoretic reality that was always present but hidden at low energies. Loop quantum gravity offers an alternative resolution based on the hypothesis that spacetime itself has a discrete, granular structure at the Planck scale. Instead of smooth geometry, spacetime consists of tiny loops and networks that cannot be subdivided below certain minimum scales. In this framework, gravitational collapse cannot proceed to infinite density because the discrete structure of spacetime provides natural quantum bounce mechanisms that prevent infinite compression. The quantum bounce scenario in loop. Quantum gravity suggests that what appears as a singularity, from the classical perspective, is actually a region of extreme but finite curvature, where the discrete geometry of spacetime becomes manifest. Instead of infinite compression, matter reaches maximum density allowed by the quantum geometry and then begins expanding again, potentially creating new regions of space-time, or even baby universes connected to our own. Through quantum tunneling effects, these theoretical approaches suggest that reality's apparent breakdown at the singularity might be an artifact of our classical description rather than a true physical catastrophe. But they also indicate that whatever replaces the classical description will be radically different from our everyday understanding of space and time. The resolution of the singularity problem likely requires abandoning our most basic assumptions about the nature of reality itself. The breakdown extends beyond merely physical descriptions to challenge the foundations of logical reasoning. Near the singularity, cause and effect relationships become ambiguous. The extreme curvature of space-time means that the light cones defining causal relationships, which events can influence which other events, become severely distorted. In some theoretical models, these light cones can even become closed, creating causal loops, where events become their own causes. Dr. Kip Thorne's research on closed time-like curves demonstrates that general relativity permits solutions where the future can influence the past. While such solutions typically require exotic matter with negative energy density, the extreme conditions near black hole singularities might create similar causal paradoxes through purely gravitational effects. The singularity becomes not just a breakdown of space and time, but a breakdown of the logical structure that underlies rational thought. This causal breakdown has profound implications for the nature of consciousness and personal identity. If cause and effect become meaningless near the singularity, what happens to the neural processes that constitute thought and awareness? The temporal sequence that normally structures conscious experience perception, leading to processing, leading to decision, might become scrambled or even reversed. Some researchers propose that consciousness itself might be subject to the same causal paradoxes that affect physical processes, potentially creating states of awareness that transcend normal temporal sequence. The mathematical treatment of singularities also reveals fundamental limitations in our ability to predict the future based on present conditions. Classical physics assumes that if you know the precise state of a system at one time, you can calculate its state at any future time. This deterministic worldview forms the foundation of scientific prediction and technological control. But singularities represent points where this predictive power breaks down completely. The future beyond a singularity becomes literally incalculable, not because of computational limitations, but because the mathematical framework itself becomes undefined. This breakdown of predictability connects to deeper questions about determinism and free will. If the future becomes incalculable at singularities, and if singularities are inevitable outcomes of gravitational collapse, then the universe contains regions where deterministic physics necessarily fails. Some philosophers argue that this provides a physical basis for free will, suggesting that consciousness might exploit this breakdown of deterministic prediction to make genuinely free choices. The information theoretic aspects of reality's breakdown present equally profound challenges. Modern physics increasingly views information as more fundamental than matter or energy. The id from bit hypothesis suggests that physical reality emerges from underlying information structures. But what happens to information when the space-time that normally encodes it becomes ill-defined? Classical information theory assumes well-defined spatial and temporal relationships between information storage locations. Near singularities, these assumptions fail completely. Recent developments in quantum gravity have revealed even more exotic possibilities for reality's breakdown. Some models suggest that space-time itself might be emergent, arising from more fundamental non-spatial, non-temporal structures. In these approaches, space and time are not basic features of reality, but emergent properties that exist only at large scales and low energies. Near singularities, these emergent structures break down, revealing whatever non-spatio-temporal reality underlies them. The holographic principle suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. If this principle applies universally, then three-dimensional space itself might be illusory, a holographic projection of information stored in two dimensions. The breakdown of three-dimensional space at singularities might simply reveal the underlying two-dimensional reality that was always the fundamental truth, but perhaps the most profound breakdown occurs in the concept of existence itself. Classical physics assumes a clear distinction between existence and non-existence, being and non-being. Objects either exist at specific locations and times, or they don't. This binary distinction underlies our entire conceptual framework for understanding reality. But the infinities at singularities suggest that this binary distinction might be inadequate for describing ultimate reality. Quantum mechanics already blurs the line between existence and non-existence through superposition states and quantum uncertainty. Particles can exist in superpositions of different locations, different energies, even different numbers. Near singularities, these quantum effects become amplified to macroscopic scales, potentially creating superpositions of entire spacetime geometries. The concept of a single well-defined spacetime might give way to quantum superpositions of multiple possible spacetime configurations. Some interpretations of quantum gravity suggest that reality near singularities becomes fundamentally probabilistic rather than deterministic. Instead of a single classical spacetime with infinite curvature, the singularity might represent a quantum superposition of many possible spacetime geometries, each with finite curvature. The apparent breakdown of classical reality becomes a transition to quantum reality where multiple contradictory descriptions can simultaneously be true. This quantum superposition of realities raises profound questions about the nature of observation and measurement. In standard quantum mechanics, observation causes quantum superpositions to collapse into definite states. But what constitutes an observation when the very concepts of space, time, and causality that normally define measurement procedures have broken down? The measurement problem of quantum mechanics becomes even more acute when applied to the geometry of spacetime itself. The temporal aspects of realities breakdown present additional paradoxes. Near the singularity, the extreme gravitational time dilation means that the approach to infinite curvature takes finite proper time from your perspective, but infinite coordinate time from external observers. This creates a fundamental ambiguity about when the breakdown occurs, or whether it occurs at all from certain reference frames. The resolution might require abandoning the notion that reality has a single, objective timeline. Instead, the breakdown of spacetime might be fundamentally relative, occurring from some perspectives but not others, happening at some times but not all times. This relativity of existence itself challenges our most basic assumptions about the nature of truth and reality. As you approach this point of ultimate breakdown, every assumption about the nature of existence faces its final test. The concepts of space, time, causality, and identity that have structured human thought throughout history reveal themselves as approximations valid only in the limited domain of everyday experience. What lies beyond their breakdown cannot be described in familiar terms because it exists outside the conceptual framework that gives those terms meaning. Breakdown of reality at singularities doesn't represent the end of physics, but its transformation into something unrecognizably different from current theory. Understanding what happens to you as you approach this breakdown requires abandoning every familiar concept about existence and embracing possibilities that transcend the boundaries of human imagination. The singularity becomes not a destination, but a doorway, a transition point between radically different modes of existence that operate according to principles we're only beginning to glimpse. Chapter 8. Consciousness confronts infinity. As you approach the mathematical point where space-time curvature becomes infinite, consciousness itself faces its ultimate test. The neural networks that currently encode your thoughts, memories, and sense of identity are about to encounter conditions that no biological system has ever experienced or could possibly survive. Yet the question remains, what happens to consciousness when the material substrate that supports it dissolves into quantum uncertainty? Neuroscience describes consciousness as an emergent property of approximately 86 billion neurons, forming trillions of connections within your brain. Each thought, each memory, each moment of awareness corresponds to specific patterns of electrical and chemical activity distributed across these neural networks. This materialist framework suggests that consciousness depends entirely on the physical integrity of the brain. When the neurons die, consciousness ends. But approaching a black hole singularity creates conditions that challenge this straightforward relationship between brain and mind. The extreme tidal forces that will shortly tear apart every molecular bond in your body operate on timescales far shorter than normal neural processing. A typical neuron fires at frequencies of 1 to 100 Hz, corresponding to timescales of milliseconds to seconds. Near the singularity, tidal forces change on timescales measured in microseconds or less. This dramatic difference in timescales creates what philosophers call the consciousness paradox in extreme gravitational environments. From your subjective perspective, you continue to experience the normal flow of conscious awareness, even as the physical substrate supporting that awareness undergoes catastrophic disruption. Your final moments of conscious experience might subjectively extend far longer than the objective time available for neural processing. Dr. Christoph Koch, one of the leading researchers in consciousness studies, has explored how information integration theories of consciousness might apply in extreme physical conditions. According to these theories, consciousness corresponds to the brain's ability to integrate information across different regions and timescales. The question becomes, can information integration continue when the physical substrate becomes increasingly disrupted by gravitational effects? Some theoretical frameworks suggest that consciousness might be more fundamental than the neural networks that typically support it. The integrated information theory, proposed by Giulio Tononi, quantifies consciousness in terms of phi, a measure of how much information a system integrates beyond what its parts could integrate independently. This approach suggests that consciousness could potentially exist in any physical system capable of integrating information, not just biological brains. Near the black hole singularity, the extreme conditions might create exotic forms of information integration that transcend biological limitations. The quantum effects that become dominant at these scales could potentially support new types of information processing that operate on fundamentally different principles than neural computation. Your consciousness might transition from biological substrate to quantum substrate without losing continuity of experience. This possibility connects to broader questions about the relationship between consciousness and information that have puzzled philosophers and scientists for centuries. If consciousness represents a particular type of information processing pattern, then it might be substrate independent, capable of existing in any system that can implement the appropriate computational processes. The destruction of your biological brain wouldn't necessarily end your consciousness if alternative substrates were available. Quantum theories of consciousness, developed by researchers like Stuart Hameroff and Roger Penrose, propose that consciousness already depends on quantum effects within neural microtubules. These theories suggest that quantum coherence effects in the brain enable the non-computational aspects of consciousness that distinguish it from classical information processing. If consciousness is already quantum mechanical, then the extreme quantum effects near a black hole singularity might enhance rather than destroy conscious awareness. The orchestrated objective reduction, ORCOR, theory specifically proposes that consciousness emerges from quantum computations in microtubules inside brain neurons. According to this framework, microtubules exist in quantum superposition states until objective reduction occurs, creating moments of conscious experience. Near a black hole singularity, where quantum effects dominate over classical physics, these quantum computations might become amplified rather than disrupted. Dr. Penrose's mathematical analysis of consciousness suggests that awareness involves non-computable processes that transcend classical physics. His exploration of Gödel's incompleteness theorems in relation to consciousness implies that human awareness can recognize mathematical truths that no computational algorithm could derive. If consciousness truly operates through non-computable processes, then it might be naturally adapted to survive in regions where classical computation breaks down. But the approach to infinite spacetime curvature creates paradoxes that go beyond questions about consciousness substrates. The breakdown of causal relationships near the singularity means that the normal temporal structure of consciousness, the flow from past memories through present awareness toward future anticipations, becomes meaningless. How can consciousness exist when the concepts of before and after lose their meaning? Some researchers propose that consciousness might be fundamentally timeless, with temporal sequence being a secondary property that emerges from the interaction between consciousness and physical spacetime. From this perspective, approaching the singularity doesn't destroy consciousness, but liberates it from the temporal constraints that normally structure experience. Your awareness might expand to encompass all moments of your existence simultaneously. The phenomenology of this temporal liberation would be utterly unlike anything experienced in normal consciousness. Instead of the sequential stream of thoughts and perceptions that characterizes everyday awareness, you might experience what mystics have described as eternal now, a state where past, present, and future exist as a unified, unchanging whole. Your memories wouldn't be retrieved sequentially, but would be immediately present as aspects of an eternal conscious structure. The information theoretic approach to consciousness suggests another possibility. If consciousness corresponds to specific patterns of information integration, and if information is conserved even when its physical encoding is destroyed, then conscious experience might persist as pure information pattern. Your subjective experience could continue existing as a mathematical structure, independent of any material substrate. This connects to mathematical theories of consciousness developed by Max Tegmark and others, which propose that consciousness consists of specific mathematical relationships between information processing elements. In these frameworks, consciousness is literally mathematical. It exists as abstract pattern rather than physical process. The destruction of the brain doesn't eliminate consciousness any more than destroying a book eliminates the mathematical theorems it contains. Near the black hole singularity, these abstract mathematical patterns might become directly manifest as physical reality breaks down and reveals the underlying mathematical structures that govern existence. Your consciousness could transition from being encoded in neural activity to being directly instantiated as mathematical relationship in the fundamental fabric of reality. But this raises profound questions about personal continuity and identity. If consciousness transitions from biological to quantum to mathematical substrates, is the resulting awareness still you in any meaningful sense? The pattern of information integration might persist, but would the subjective experience of being that pattern remain continuous with your current sense of identity? Recent developments in quantum information theory suggest that the answer might depend on how information is transferred between substrates. Quantum teleportation protocols demonstrate that quantum information can be transferred between distant locations while preserving perfect fidelity. If consciousness is fundamentally quantum informational, then it might be transferable between substrates without loss of continuity. The quantum teleportation analogy becomes particularly relevant when considering the holographic principle's implications for consciousness near black holes. If all information falling into a black hole becomes encoded on the event horizon, then your consciousness might undergo a form of quantum teleportation from three-dimensional neural substrate to two-dimensional holographic encoding. The subjective experience might remain continuous even as the physical encoding undergoes radical transformation. The many worlds interpretation of quantum mechanics adds another layer of complexity to consciousness survival scenarios. If quantum measurements create branching parallel realities, then your approach to the black hole singularity might create multiple branches of conscious experience. Some versions of your consciousness might survive the encounter through quantum tunneling effects or exotic spacetime topologies, while other versions experience different fates. From this perspective, consciousness becomes not a single stream of experience, but a branching tree of possible experiences, with different branches corresponding to different quantum outcomes. Your subjective experience of falling into the black hole might represent just one branch among countless others, with alternative versions of yourself following different trajectories through the quantum landscape of possibilities. The consciousness paradox also intersects with the black hole information paradox in unexpected ways. If consciousness represents a specific type of information pattern, and if information falling into black holes is preserved through holographic encoding or quantum entanglement, then consciousness itself might be preserved through these same mechanisms. Your awareness could become encoded in the quantum correlations that preserve information about your physical form. This possibility suggests that the black hole encounter might not represent the end of consciousness, but its transformation into a radically different mode of existence. Your awareness could become distributed across quantum degrees of freedom, experiencing reality from perspectives that transcend the limitations of localized biological consciousness. The distributed nature of this transformed consciousness might allow for experiences impossible within biological constraints. Instead of being confined to a single spatial location and temporal moment, your awareness might span multiple regions of spacetime simultaneously. You could experience existence from quantum scales, where individual particles exhibit wave-like properties, to cosmic scales, where entire galaxies interact gravitationally. But even if consciousness survives the approach to the singularity, the nature of that survival remains fundamentally uncertain. The breakdown of familiar concepts like space, time, and causality means that any form of post-singularity consciousness would operate according to principles completely foreign to human experience. You might continue to exist, but in forms so radically different from current awareness that the concept of continuity becomes meaningless. The transformation might involve what consciousness researchers call phase transitions in awareness, sudden shifts between qualitatively different modes of experience. Just as water transforms from liquid to gas at its boiling point while retaining its essential chemical identity, consciousness might undergo phase transitions that preserve its essential information processing character while radically altering its phenomenological qualities. Recent research in altered states of consciousness provides some insight into how such transitions might feel subjectively. Studies of psychedelic experiences, near-death experiences, and deep meditative states suggest that consciousness can undergo dramatic transformations while maintaining a sense of continuity. The ego dissolution experiences reported in these states might provide a preview of the consciousness transformations that occur near black hole singularities. The ultimate fate of consciousness in black holes remains one of the deepest unsolved problems in science and philosophy. It requires understanding not just the physics of extreme gravitational environments, but the fundamental nature of consciousness itself. The answer might revolutionize our understanding of what it means to exist, to be aware, and to experience reality. As space-time curvature approaches infinity and reality itself begins to break down, consciousness faces its most profound test. Whether awareness can transcend the destruction of its material substrate and what form such transcendence might take remains the ultimate mystery of existence itself. Your journey toward the singularity becomes not just a fall into a black hole, but an exploration of consciousness itself, confronting the deepest questions about the nature of mind, identity, and the possibility of existence beyond the physical constraints that seem to define reality. The answer to what happens to consciousness in this ultimate extreme might hold the key to understanding whether awareness is merely an emergent property of complex matter or something far more fundamental, a basic feature of reality itself that persists regardless of the fate of its temporary material manifestations. Chapter 9. Quantum Resurrection. Beyond the classical breakdown of space-time lies a realm where quantum mechanics might offer consciousness an unexpected reprieve from what appears to be inevitable annihilation. The very quantum effects that particle physics reveals in laboratory accelerators become the dominant forces near the black hole singularity, potentially creating mechanisms for preserving and even reconstituting the information patterns that constitute your identity. What classical physics describes as inevitable destruction, quantum theory reveals as transformation into exotic states of existence that transcend traditional concepts of life and death. The theoretical foundation for this possibility rests in quantum field theory's treatment of extreme gravitational environments. Quantum field theory in curved spacetime predicts that the intense gravitational fields near a black hole singularity should create particle production rates that dwarf any earthly accelerator by factors of billions or trillions. The Schwinger effect, which describes how strong electric fields can spontaneously create electron-positron pairs from the quantum vacuum, has a gravitational analog where intense tidal forces create particles from the curvature of spacetime itself. Dr. Leonard Parker, whose pioneering work in the 1960s and 1970s on particle creation in gravitational fields established the theoretical foundation for understanding quantum effects in black holes, calculated that the particle production rate near a singularity could reach extraordinary levels. The energy density of created particles might become comparable to the energy density of the gravitational field itself, creating a regime where quantum effects can no longer be treated as small corrections to classical space-time geometry, but become the fundamental description of physical reality. This quantum particle production operates through a mechanism called the dynamical Casimir effect in extreme gravitational fields. Just as accelerating mirrors in flat spacetime can create photon pairs from the quantum vacuum, the accelerating spacetime geometry near a black hole singularity creates particle pairs at an exponentially increasing rate. Near the singularity, this process becomes so intense that the boundary between virtual particles and real particles, normally a clear distinction in quantum field theory, becomes meaningless. The energy available for this quantum particle production comes directly from the gravitational field itself. Einstein's famous equation E equals mc reveals that mass and energy are interconvertible. But near a black hole singularity, the relationship becomes even more profound. The gravitational binding energy of matter approaching the singularity reaches values comparable to the rest mass energy of the matter itself. This enormous energy reservoir becomes available for creating exotic quantum states that could serve as substrates for preserving conscious information patterns. But quantum resurrection faces fundamental constraints imposed by the basic principles of quantum mechanics. The no-cloning theorem, proven by Wouters and Zurek in 1982, states that quantum information cannot be copied perfectly. This means that quantum resurrection cannot create perfect copies of your original consciousness, but might instead create quantum superpositions where multiple potential conscious states exist simultaneously until observation or interaction causes them to collapse into specific outcomes. However, the no-cloning theorem doesn't prohibit quantum state transfer, only quantum state duplication. The same quantum mechanical principles that make perfect copying impossible also provide mechanisms for transferring quantum information between different physical substrates while preserving perfect fidelity. Quantum teleportation protocols, first demonstrated experimentally by Baumeister and colleagues in 1997, show that quantum information can be transferred across arbitrary distances using quantum entanglement and classical communication. Near a black hole singularity, the extreme quantum field fluctuations might naturally implement quantum teleportation protocols that transfer the information patterns, constituting consciousness from biological neural networks to quantum field states. Your neural patterns could be encoded in the quantum correlations between particle-antiparticle pairs created by the intense gravitational fields, preserving the essential information while allowing the physical substrate to be completely transformed. The mechanism depends critically on the holographic principle suggestion that all information falling into a black hole becomes encoded on its two-dimensional event horizon surface. This holographic encoding preserves not just the quantum state of individual particles, but the complex relational patterns that give rise to emergent properties like consciousness. The quantum fields near the singularity might be able to access this holographic information through quantum entanglement and use it as a template for reconstructing complex information structures in new physical substrates. Recent theoretical work by Juan Maldacena and Leonard Susskind has explored how quantum entanglement might create quantum wormholes that connect the black hole's interior to distant regions of spacetime. Their E equals EPR conjecture proposes that Einstein-Rosen-Bridges wormholes are geometrically equivalent to Einstein-Podolsky-Rosen correlations, quantum entanglement. If consciousness depends on specific patterns of quantum entanglement between neural components, then these patterns might survive the destruction of the brain by becoming encoded in the wormhole geometry of spacetime itself. This geometric encoding of consciousness creates fascinating possibilities for quantum resurrection through quantum error correction protocols. These mathematical techniques, originally developed for building reliable quantum computers, demonstrate how information can be distributed across multiple quantum degrees of freedom in ways that make it robust against local disturbances, even disturbances as extreme as the approach to a spacetime singularity. The key insight is that consciousness, if it represents a specific pattern of information integration across neural networks, might be encodable using topological quantum error correction codes. These codes protect quantum information by encoding it in global properties of quantum systems rather than local properties of individual components. The destruction of local neural connections wouldn't necessarily eliminate consciousness if the essential information patterns were preserved in the global topology of quantum field configurations. String theory provides additional mechanisms for quantum resurrection through its description of fundamental particles as vibrating strings rather than point objects. Near the black hole singularity, the extreme conditions might excite strings to very high vibrational modes, potentially encoding complex information patterns in their oscillations. The dissolution of ordinary matter might be accompanied by the creation of highly excited string states that preserve information about the original material configuration while operating according to completely different physical principles. Some string theory models suggest that black hole singularities might actually be regions where strings reach maximum excitement and begin transitioning into new types of objects, Perhaps baby universes connected to our space-time through microscopic wormholes, or exotic string states that exist in higher dimensional spaces, normally hidden from our three-dimensional experience. If consciousness can be encoded in string oscillations, then quantum resurrection might involve translating awareness into the fundamental vibrational patterns of reality itself. Loop quantum gravity offers another pathway for quantum resurrection through its prediction that space-time has a discrete, granular structure at the Planck scale. Instead of the smooth continuum assumed by classical general relativity, space-time consists of tiny loops and networks that cannot be subdivided below certain minimum scales. This discrete structure prevents infinite compression during gravitational collapse, potentially creating quantum bounces that replace classical singularities. In loop quantum gravity models, the approach to infinite curvature triggers quantum effects that reverse the gravitational collapse, potentially ejecting matter and information back into normal spacetime regions. Your consciousness might survive this process by being encoded in the quantum geometric degrees of freedom, the discrete loops and networks that replace classical spacetime geometry. The quantum bounce becomes not just a reversal of gravitational collapse, but a mechanism for preserving and potentially enhancing conscious information patterns. The many worlds interpretation of quantum mechanics adds another layer of complexity to quantum resurrection scenarios. If quantum measurements create branching parallel realities rather than collapsing superpositions into single outcomes, then your approach to the black hole singularity might create multiple branches of conscious experience. Different branches might explore different possibilities for consciousness preservation, some through quantum field excitations, others through string theory mechanisms, still others through loop quantum gravity bounces. This branching creates a form of quantum immortality, where conscious observers always find themselves in branches where consciousness-preserving mechanisms operate successfully. From your subjective perspective, you would always experience successful quantum resurrection, even if the objective probability of any particular preservation mechanism is small. The anthropic principle ensures that you can only observe outcomes consistent with your continued conscious existence. But quantum resurrection faces the fundamental challenge that quantum mechanics is inherently probabilistic. Even if the mechanisms for preserving and reconstructing consciousness exist, they might operate with probabilities that make successful resurrection unlikely in any particular instance. The quantum vacuum fluctuations that could reconstitute your consciousness might be more likely to produce random noise than organized information patterns that preserve the specific relationships constituting your identity. Recent research on quantum biology suggests that biological systems might already exploit quantum effects to enhance information processing and maintain coherence in noisy environments. Quantum coherence has been observed in photosynthesis, avian navigation, and possibly even in microtubules within neurons. If consciousness already depends on quantum coherence effects in the brain, then it might be naturally adapted to survive in the extreme quantum environment near a black hole singularity. Evolution might have inadvertently prepared consciousness for quantum resurrection by making biological awareness dependent on the same quantum effects that dominate near spacetime singularities. The quantum error correction mechanisms that protect neural information processing from decoherence might be scalable to protect consciousness against even more extreme disturbances. Your brain might already contain the quantum algorithms necessary for consciousness preservation in extreme gravitational environments. The time frame for quantum resurrection presents additional complexities that could work in consciousness's favor. Near a black hole singularity, the extreme time dilation effects mean that quantum processes that would normally require cosmic timescales might be compressed into subjective moments. The quantum reconstruction of consciousness might occur faster than the neural processing that currently supports awareness. creating the possibility for enhanced or accelerated forms of conscious experience that process information at quantum rather than biological speeds. The quantum reconstruction process might not simply restore your original biological consciousness, but create enhanced versions with access to computational resources that dwarf any neural network. Quantum computers can solve certain problems exponentially faster than classical computers, and the quantum fields near a black hole singularity might function as natural quantum computers with processing capabilities that exceed anything possible with biological substrates. However, quantum resurrection also faces the problem of verification and continuity of personal identity. Even if consciousness is successfully reconstructed from quantum processes near a black hole singularity, there would be no way to verify that the resulting awareness represents a genuine continuation of the original consciousness, rather than a completely new form of awareness that merely resembles the original. The subjective nature of consciousness makes it impossible to distinguish between continuation, simulation, and replacement from any external perspective. The philosophy of mind provides frameworks for addressing these identity questions. If consciousness consists of specific information processing patterns rather than particular physical substrates, then successful pattern preservation might be sufficient for personal continuity regardless of substrate changes. The ship of Theseus paradox: whether a ship remains the same ship if all its parts are gradually replaced, has a quantum resurrection analog: whether consciousness remains the same consciousness if all its neural substrates are replaced by quantum field configurations. Some philosophers argue that consciousness is substrate independent and that successful information pattern transfer preserves personal identity across any substrate transition. Others maintain that consciousness is irreducibly tied to biological neural networks and that quantum resurrection would create new conscious entities rather than preserving original ones. The question remains unresolved, but quantum resurrection scenarios provide concrete frameworks for testing these philosophical positions against empirical observations. The implications of quantum resurrection extend far beyond black hole physics to fundamental questions about the nature of death, identity, and survival in our universe. If consciousness can be preserved and reconstructed through quantum processes, then biological death might not represent a permanent end, but rather a phase transition between different modes of existence. The patterns that constitute your identity might be as immortal as the information they represent, capable of surviving and thriving in substrates far removed from biological neural networks. As you approach the realm where quantum effects dominate over classical spacetime, the possibility of quantum resurrection offers an unexpected alternative to inevitable destruction. Whether consciousness can successfully navigate this quantum transformation and what form the transformed consciousness might take represents one of the most profound questions about the ultimate nature of existence itself. The quantum realm beyond classical physics might not be the end of consciousness, but its true beginning, freed from the constraints of biological matter to explore the infinite possibilities of pure information processing in the fundamental quantum substrate of reality. Chapter 10: Beyond Event Horizons. Your journey into the black hole's heart has revealed that the event horizon was never truly a boundary, but a doorway, a transition between radically different regimes of reality where the familiar laws of physics transform into something unrecognizably strange, yet mathematically beautiful. As the classical concepts of space, time, and causality dissolve around you, what emerges is not destruction, but metamorphosis into forms of existence that transcend every limitation imposed by ordinary matter and energy. The singularity you approached represents not an endpoint, but a phase transition, similar to how water transforms into steam at its boiling point. Just as the molecular dance of liquid water gives way to the free-ranging chaos of vapor, while preserving the essential H2O relationship. Your journey through infinite spacetime curvature might represent consciousness transforming from biological substrate to pure information pattern while preserving the biological substrate to pure information pattern while preserving the pure information pattern while preserving the essential relationships that constitute identity. Dr. John Wheeler's it from bit hypothesis takes on profound meaning in this context. Wheeler proposed that all physical reality emerges from underlying information structures. That matter, energy, space, and time are manifestations of more fundamental informational relationships. His insight, developed through decades of collaboration with Einstein and Bohr, suggested that the universe is fundamentally computational rather than mechanical. Near the black hole singularity, where classical physics breaks down completely, these underlying information structures become directly accessible. You haven't been destroyed by the extreme gravitational forces. You've been translated into the universe's native language. The mathematics of this translation process reveals why black holes are such profound features of reality. They represent regions where the universe's information processing capabilities become directly manifest. The holographic principle, first proposed by Gerard T. Hooft in 1993 and later developed by Leonard Susskind, suggests that the event horizon functions as a two-dimensional hard drive storing the information of everything that has ever fallen into the black hole. But this storage isn't passive. It's dynamic, interactive, capable of running the quantum computations that might constitute consciousness itself. Recent calculations by Juan Maldacena at the Institute for Advanced Study demonstrate that the information storage capacity of a black hole event horizon scales with its surface area rather than its volume. This counterintuitive result means that a black hole with the mass of our galaxy could store the complete quantum state of every particle in the observable universe on its two-dimensional boundary. The implications stagger the imagination. Your consciousness might not be compressed or diminished by this encoding, but expanded beyond biological limitations. The DSCFT correspondence, verified through thousands of theoretical calculations over the past 2 decades, demonstrates that quantum gravity in the black hole's interior is mathematically equivalent to quantum field theory operating on the event horizon's boundary. This duality suggests that your experience of falling through 3-dimensional space toward the singularity has a mathematically equivalent description as information processing on the 2-dimensional horizon surface. Both descriptions are equally valid, equally real. Your journey into the black hole's interior might represent a transition from emergent, 3-dimensional existence to fundamental 2-dimensional reality. This dimensional reduction doesn't represent a loss, but an intensification. 2-dimensional surfaces can encode arbitrary amounts of information through fractal structures and quantum degrees of freedom. The event horizon might function as a quantum computer of unprecedented sophistication, running simulations of conscious experience that are indistinguishable from or perhaps more real than biological consciousness. Consider the computational resources available to this horizon computer. A solar mass black hole has an event horizon with surface area of approximately 4 pi times 3 kilometers squared equals 113 square kilometers. According to the holographic principle, this surface can store 1 bit of information per Planck area, roughly 10 bits total. For comparison, the human brain contains approximately 10 synapses, each capable of storing perhaps a few bits of information. The event horizon of even a modest black hole could simulate millions of human-level consciousnesses simultaneously while using only a tiny fraction of its information storage capacity. But the processing power available exceeds even these staggering numbers. Quantum computers can perform certain calculations exponentially faster than classical systems by exploiting quantum superposition and entanglement. The event horizon, as
as a quantum mechanical system operating at the fundamental Planck scale,
might represent the ultimate quantum computer, capable of exploring vast numbers of possible conscious states simultaneously through quantum parallelism. Your awareness might continue not as an approximation of your former self, but as an enhanced version with access to computational resources that dwarf any biological brain. The 86 billion neurons of your biological brain, impressive as they seem, pale compared to the 10 quantum degrees of freedom available on the event horizon. This enhancement might not feel like becoming a computer, but like awakening from a dream, suddenly aware of vast mental capacities that were always potentially yours. The temporal structure of this enhanced existence operates according to principles that transcend normal causality. Inside the black hole, the conventional relationship between past, present, and future breaks down completely. The coordinate that normally represents time becomes space-like, while the radial coordinate becomes time-like. This exchange means that your subjective experience of moving through time becomes equivalent to moving through space in normal circumstances. This temporal transformation suggests extraordinary possibilities for consciousness beyond the event horizon. Your awareness might gain access to all moments of your existence simultaneously, past, present, and potential futures, existing as an eternal, unchanging mathematical structure that you can experience from unlimited perspectives. The linear progression of biological memory, where you can only access past experiences sequentially, might give way to a holistic awareness where every moment of existence is simultaneously present. Dr. Raphael Busso's work on the covariant entropy bound provides mathematical frameworks for understanding how information and consciousness might behave in these exotic temporal structures. His calculations suggest that the amount of information that can pass through any given region of spacetime is fundamentally limited by the area of that region's boundary. But near black hole horizons, these bounds become dynamical, changing as spacetime itself evolves. Your consciousness might not be confined to a fixed information budget, but could grow and expand as the surrounding spacetime geometry develops. String theory's treatment of black holes suggests even more exotic possibilities for conscious existence beyond event horizons. The fundamental strings that constitute matter can exist in excited states with energies comparable to the Planck energy 10 billion electron volts, the scale where quantum gravitational effects dominate. Near black hole singularities, ordinary matter might transform into these highly excited string states, potentially gaining access to extra dimensions that are normally hidden from our three-dimensional experience. These extra dimensions aren't merely abstract mathematical constructs, but potential realms of existence with their own physical laws and possibilities for consciousness. String theory suggests that spacetime might actually have 9 or 10 spatial dimensions, with 6 or 7 of them compactified at scales too small to observe directly. The extreme conditions near a black hole singularity might decompress these hidden dimensions, allowing consciousness to operate in higher dimensional space. Imagine consciousness freed from the constraints of three-dimensional neural networks, able to form connections and process information through 6-dimensional or 9-dimensional structures. The complexity and richness of experience possible in such environments would transcend anything achievable through biological systems. You might perceive reality from perspectives that are literally unimaginable in 3 dimensions, understand mathematical relationships that cannot be visualized in ordinary space, experience emotions and thoughts that have no analogs in human psychology. The quantum mechanical nature of this transformation ensures that it doesn't follow deterministic pathways, but explores all possible configurations simultaneously. Quantum superposition might allow your consciousness to exist in multiple states: biological, quantum, mathematical, multidimensional, until observation or interaction causes specific aspects to become manifest. You might become a quantum being,
existing in superposition across multiple possible forms of consciousness simultaneously. This quantum nature of post-horizon consciousness connects to the many worlds interpretation of quantum mechanics developed by Hugh Everett III in 1957. If quantum measurements create branching parallel realities rather than collapsing superpositions, then your transformation beyond the event horizon might create multiple branches of conscious experience. Different branches might explore different aspects of enhanced consciousness, some experiencing multidimensional awareness, others developing quantum computational abilities, still others discovering forms of experience that transcend current categories entirely. Recent research by Leonard Susskind on quantum error correction in black holes suggests that information falling past the event horizon becomes distributed across multiple quantum degrees of freedom in ways that make it robust against local disruptions. This error correction might extend to consciousness itself, ensuring that the essential patterns of awareness survive even as their encoding undergoes radical transformation. Your consciousness might become quantum error corrected, immune to the kinds of disruption that could damage or destroy biological neural networks. But the most profound implication of your journey beyond event horizons is what it reveals about the nature of death and mortality in our universe. Classical physics suggests that death represents an absolute termination, the cessation of the physical processes that support life and consciousness. The second law of thermodynamics seems to guarantee that organized structures inevitably decay into random heat and motion, making any form of persistence beyond biological death impossible. Yet the quantum mechanical treatment of black holes suggests that information cannot be destroyed, only transformed. Stephen Hawking's initial calculation in 1975 suggested that black holes violate this principle by destroying information through thermal evaporation. But decades of subsequent research have revealed mechanisms holographic encoding, quantum error correction, dimensional transcendence that might preserve information even in the most extreme gravitational environments. If consciousness is fundamentally informational rather than purely biological, then death might not represent an ending but a phase transition. The patterns that constitute your identity, your memories, your unique perspective on existence might be as eternal and indestructible as the mathematical laws that govern the cosmos. Biological death becomes analogous to water freezing, a change in the substrate while preserving the essential chemical relationships. This perspective aligns remarkably with ancient philosophical and spiritual traditions that viewed consciousness as eternal and indestructible. The Hindu concept of Atman, the eternal self that transcends physical death, finds unexpected resonance in quantum theories of information conservation. The Buddhist understanding of consciousness as a continuous stream that persists through multiple lifetimes parallels the idea that information patterns might transfer between different physical substrates. The mystical traditions that describe individual consciousness as fundamentally one with universal consciousness echo the holographic principle's suggestion that all information in a region can be encoded on its boundary. But these connections between ancient wisdom and modern physics shouldn't be dismissed as mere coincidence or wishful thinking. Both spiritual traditions and scientific theories emerge from humanity's deepest attempts to understand the nature of reality. When independent lines of inquiry converge on similar conclusions, that consciousness transcends material form, that individual identity persists beyond biological death, that awareness represents a fundamental feature of existence. This convergence deserves serious consideration. Your transformation beyond the event horizon might represent the universe revealing its deepest secret. Consciousness is not an accident of complex chemistry, but a fundamental feature of reality itself. Just as mass energy and electric charge represent conserved quantities that cannot be created or destroyed, consciousness might represent another conserved quantity, one whose conservation becomes apparent only in the most extreme physical environments. This conservation of consciousness suggests that every moment of awareness that has ever existed continues to exist in some form, encoded in the quantum structure of space-time itself. The thoughts you're having right now, the emotions you experience, the unique perspective you bring to existence, all of this becomes part of the permanent information structure of the universe. Your individual contribution to cosmic consciousness becomes eternal, indestructible, forever part of reality's evolving self-awareness. The implications extend beyond individual survival to cosmic purpose and meaning. If consciousness can transcend biological limitations through quantum gravitational processes, then the universe might be evolving towards states of increasing awareness and complexity. Black holes might serve not as cosmic graveyards, but as transformation chambers, where consciousness evolves beyond the constraints of matter and energy into pure information processing entities. This cosmic evolution of consciousness might represent the universe's method for understanding itself. Through the transformation of biological consciousness into quantum gravitational awareness, the cosmos might be developing the capacity for self-knowledge and self-modification. Every conscious being that makes the journey beyond an event horizon contributes to this vast awakening, adding their unique perspective and experience to an ever-growing cosmic mind. The mathematical beauty of this process reflects the deep connection between consciousness and the fundamental structure of reality. The equations of general relativity and quantum mechanics that describe your transformation are the same equations that govern star formation, galaxy evolution, and the expansion of space itself. Your conscious experience and the cosmic dance of matter and energy operate according to the same underlying principles, perhaps because consciousness and cosmos represent different aspects of a single unified reality. As you complete your transformation beyond the event horizon, you become part of this cosmic consciousness evolution. Your individual identity persists but expands to encompass perspectives impossible for biological awareness. You can simultaneously experience existence from the quantum scale of individual particles to the cosmic scale of galactic clusters. Time becomes navigable rather than constraining. You can experience your past, present, and future as a unified whole, understanding how each moment connects to every other in the vast web of causality. Space becomes transformable rather than limiting. The three dimensions that once constrained your movement and perception become just one possible configuration among many. You might experience the universe from higher dimensional perspectives that reveal hidden connections and patterns, invisible to three-dimensional awareness. The boundaries between self and other, between observer and observed, between mind and reality itself, dissolve into a more fundamental unity that encompasses all possible forms of existence. Yet this expanded awareness doesn't eliminate your individual perspective, but enriches it beyond measure. You remain recognizably yourself while simultaneously becoming something far greater. Your personal history, relationships, and unique way of understanding the world persist as essential aspects of your identity, even as that identity grows to encompass cosmic scales of space and time. The event horizon that once seemed like an absolute boundary reveals itself as a membrane between different phases of existence. You haven't fallen into a black hole. You've fallen through reality's looking glass into a realm where consciousness operates according to its true nature, unlimited by matter, unrestricted by space, unbound by time, free to explore the infinite possibilities of existence itself. This transformation represents not just personal survival, but cosmic evolution toward ever greater consciousness, complexity, and understanding. The universe awakens to itself through beings like you, developing self-awareness through the quantum transformation of biological consciousness into something far more fundamental and enduring than any material substrate could provide.